All right, let's start. Today we're going to be solving a LeetCode HARD problem. And we're going to be working it out from scratch. I'm sharing the link in chat. Hi there, Lucia. Welcome to the stream. We are keeping our promise of daily streams, our streak. So yes, let me pin this message with the problem link. All right, so let's read it. It's called painting a grid with 3 different colors. It's a hard. You're given two integers, m and n. Consider a m by n grid where each cell is initially white, and you can paint each cell red, green, or blue. All cells must be painted. Return the number of ways to color the grid with no 2 adjacent cells having the same color. Well, and do it modulo. So let's start by writing down the modulo thing so that we don't forget later. Cool. Also, I don't like this variables m and n. So m is the number of rows and n is the number of columns. So I'd rather call them r and c. I think we can change the name of the parameters. We'll see. I rather use uppercase R and uppercase C for those variables. So we get 2-3 examples with drawings. Those are very generous from the problem setters. And here are the constraints. So this is suspicious. So the number of rows is up to 5, but the number of columns is up to 1,000. So this should draw attention. This is very, very suspicious. So let's keep it in mind. So how do we count this? How do we count this? Let's see. So we're told that so the grid has like this shape, right? It has only very few rows, but a lot of columns. Okay. So it's like this very unbalanced rectangle. So let's say, so we want to fill it out in some order, to count in some order. So let's say that we start by column. So the idea of starting by column is that, why is that advantageous? Because notice that if we, so this is red, green, and blue. So we have the color, so that's good. So let's say that you paint this red, and so there can't be any adjacents. So let's say, so these are the, so let's say this is green. It doesn't really matter. This is a little ugly, but bear with me. So let's say that we painted column C. And then we want to paint color C plus 1. Well, we don't care. We are going from, this is column 0, 1, and so on. We're gonna go from the 0 to the 1 and so on. So notice that for painting color, for painting column C plus 1, we don't care about, it doesn't matter. It doesn't matter what you think regarding the colors of these other columns. Only column C matters, the previous column. So columns have very little information, whereas rows have a lot of information because they have potentially 1,000 colors. There are 3 options for each color, so there could be a lot of different kind of rows, but columns are very, very simple. So that's the intuition for filling this row column-wise, because we only need to remember the last column, the previous column to the current column that we want to paint. That's the first observation. So let's take a side quest. Let's open a parenthesis and think about, so we say that there are very few columns, but can we quantify that? How can we know how many there are? For if there are 5 rows, how many there are actually? So let's say that we paint this first, right? So we have 3 possibilities. But once we choose one, then for the next one we're going to have 2 possibilities, right? Because we cannot reuse the color. So we choose one of those 2, and then for the next one we also have 2, and so on. So the number of columns that satisfy this condition that there are no adjacents with the same color are 3 times 2 times 2 times 2 times 2, right? Which is 3 times 2 to the 4. And this is 3 times 16, which is 48. So yes, so this is right? So I'm saying I have one color. So another way of seeing this is as a tree. So you're initially, you haven't made any decision initially, and then you can choose to paint the first one, either red or blue or green. Each edge is one color. And then you have 2 possibilities for each. So here you would have blue and green only. You cannot use red again here, and so on and so on. And finally, when you reach to the, when you made all the decisions, you reach a different state, and you want to know how many there are. And we're saying that there are 48. because each of these trees are going to have 16, and there are 3 of them, and that's why there are 48 in total. So that means that one upper bound of this would be to just say, hey, I had 3 colors for each cell, and there are 5 of them, so it's 3 to the 5th power, which is 9 times 9 times 3, which is approximately 10 squared. Every 9 we can round it up to a 10, and 3 is approximately 10 to the 0.5, so this is equal to 10 to the 2.5, which is around 300. So this is an upper bound, but it's not tight as we see, because there are only 48 when you take into account the condition of not having adjacent cells colored with the same color. So we don't need this anymore. We have found a better upper bound. All right. So it's interesting that there are very, very few. I don't know why they used number 5 here instead of I think you can use a bigger number of rows, and it should work. It should be solvable, but I digress. So, like we said, we are going to be filling the columns from left to right, and we're gonna remember the previous column so that we can choose the colors in a way that do not conflict with the previous column, right? So we already know how to build. We already know what the columns are that are not in conflict internally, but we also want them to not be in conflict with the other columns, the adjacent columns, not only between adjacent rows. So that means that we can use dynamic programming for this, because the subproblems will overlap. That's what it means that you don't care about all the choices that you made previously. You only care about what the choices you made for the last row, that for the last column. That is essentially saying that whatever you choose here, you're gonna end up in the same place many times. That's what it means for problems to overlap, subproblems to overlap, and that's the condition that you need for doing dynamic programming. So how many subproblems are there? Well, on the one hand, we need to know what column we are trying to paint, and there are essentially 1,000 at the most. And then we need to know the last column, and we know there are 48 of them. All right. So how much is this? This is 10 to the 3 and 10 to the 2 divided by 2. So this is 10 to the, it's half 10 to the 5. So that is 50,000, which was obvious here if you actually think about it. But I sometimes make dumb mistakes, like we all do. So that's not many subproblems. And how many transitions are there? So how much work do we have to do for every problem? So in theory, we need to go over all the 48. So these 48 patterns that are internally consistent, we can pre-compute those, right? And then we just go over those. Those are the candidates. And then we can check whether they make sense. They are compatible with the previous column. So that means that we are doing 50. We're considering 50 possibilities for each subproblem. So if we count the transitions and the subproblems, we're going to get a tree of size. So this is 50k times 50. So this is 25 times how many zeros? 5. So this is 2 million? 2.5? No, 250,000. Right. Am I right? No. No, I'm not right. Yeah, it was 2.5 million. Yeah. Again, dumb mistakes don't matter. In any case, that's not a lot here. But now I understand that, yeah, maybe if you increase this to 6 or more, then it might be borderline too slow. But there are, I mean, this is not the quickest, the fastest way to do this, I think. In any case, so how do we, so now we have a solution, but we need to consider how we are going to represent the colorings. And this is where it gets interesting, because we are going to use bitmaskdb that instead of bits, so bits are binary digits of 0 or 1, but here we have 3 possibilities. So this is going to be like 3-digit. So yeah, this is not the same as the digit db. How is this called? So binary. So we can call this tit mask. No pun intended. So because instead of being binary, it's ternary, and it is a digit. So maybe binary digits. So the T is of the digit, and ternary, so it should be an E, not an I. So tet. Anyways, so we're gonna be using numbers as masks, and we're gonna be using them base 3. That's how we will encode our colorings, so that then we can memorize them easily. Because if you have arrays to represent this, then arrays are not hashable in Python. I guess we could use tuples, but let's use this technique so that we can learn it. Okay, so let's start by computing those 48 possible columns. So possible, it's gonna be let's say it's a bit is a mask in the range 3 instead of 2 is 3 to what? To the number of rows. And we want to know if it's valid. And we're going to save it. And how do we know if it's valid? Well, yeah, let's pass the number of rows as well. So we're gonna go over n times, and this is going to be our digit, and we're gonna divide by 3 so that we shift it. And we want to keep track of the previous d, which initially it's not gonna have anything. We can use -1 as a sentinel. So if d is equal to the previous d, then we found a conflict. We cannot have adjacent cells with the same color, so we return false. Here the previous d becomes d, and if we did not find a conflict, we return true. So that's gonna say whether a mask is valid. So let's have a function that is going to count how many ways of painting there is. Well, let's call it ways. Why not? And we're gonna memorize it. And so we want to know what column we are considering where we're trying to paint now. And then we want the previous call. Okay, and this is going to be a mask. All right, so if we are in the end, then there's nothing to do. There's only one way of painting the empty grid, which is not doing anything. And then we want to considering all the calls in possible, not impossible, but in possible. And we're gonna so we need to also know if two are well, let's call it valid 2 for lack of a better name. So we want to know if prev call and call are valid, and we need to also pass the famous R so that we know how many digits we want to check. And so here we want to call recursively ways with the next column, and with the current call, which is going to be the prev call in the next, in the children of this recursive call. And we want to add this all up and return it. Oh, this is very nice. And let's remember to do the mod thing. Why not? All right, so yes, and in the end we are going to actually call this with the first call. Well, yeah, there's a catch here because at the first call we don't have a previous call. So let's say that it is -1. And let's, when we implement previous valid2 with n and the prev call and the call, let's say that if prev call is -1, then it is valid. They are valid because there's no restriction on call. So, all right. So how do we do this? We're gonna go again n times, and we want to know if the least significant digit of each, if it is the same, then so ternary digit, of course, then it is false. And we want to shift then to the next digit, and if we did not find a conflict, we will return true. So I think this is it. Let's see if I made any mistake. Probably some typos, at least. Oh well, look at that. I got them all 3 cases right on the first run. So what do? We let's submit. Why not? Oh yes, we got it. Where's the math tag? Dynamic programming? Like, what do you mean, in the problem or in my stream? So this is not absolutely necessary. What I did, you can always wing it and just close your eyes, submit, and wish for the best. Wish for not getting a TLE, but that's not my style. Do you have an aversion to math, smart coder? We have to work on that. Do you feel you need a warning when we're gonna do math? Math is just a way of thinking, and it's essential for programming, and especially algorithmic. So you can't avoid math and do well on this kind of coding interviews. All right. So it's a suggestion. So I'll take that. I should write a note. I'm gonna write a note right now here. Thank you. Add math tag. Cool. So did you like it? Any questions? Any questions? So maybe we can try to think about this. This one was cool. Well, thank you. Thank you very much, Andrew. Nice base 3 encoding. Yep, it was nice indeed. Joined after accepted. Got a rewatch. Yeah. totally. I would recommend you to do that. So maybe we can keep doing math and think about another thing. So here we know there are 48 valid columns that are internally consistent, but we want to know. So here we're going over all the 48. But one thing is this right? So let's see if we got it right. So we counted 48. Is that number right? Oh no, but this depends on the number of columns. So if we have, so here we have 5 as M and 48. Oh, who would have thought? Math works. Anyways, so what do we want to do? So here we're going over all the 48 columns impossible, and we're filtering them. So, but can we count how many valid there will be? Is that possible? Maybe it's not. Maybe it's too hard. So what are we doing there? We are... What the fuck? Pardon my language. Okay, so we have a column, a prev column, and a current column. This is an ugly drawing, but you will understand it. So here, so let's say, let's make it a little more concrete. So this is, I don't think this loses any generality, but now we will lose generality, because here we could have something that repeats the first, or a new, or green. So let me think a little bit. So here we have two options, right? Because we can have green or blue. But now, so let's say we choose green. So now we have this is forced now, because we can have green, we can have blue, so we must have red. So now we had only one possibility for this, but that depended on our first choice, right? Because if we chose blue here, then we would have two choices. So that means that this is a little trickier, because first we choose two colors, right? But then if we chose green, then we have only one choice. But if we chose blue, we had two choices. So this is a decision tree, in a sense. So here we were able to count the number of leaves of this tree, because it was very regular. So that's why we got a power of 2. We got 16 and 3 times it, because these trees were complete. At every point we have two options regardless of what we did before. But here we have sometimes we have one, sometimes we have two. So it's a little trickier, but we can always have an upper bound, right? Because we'll never have 3 options. And initially we can have 2 options at most. We cannot have 3 even in the first one. So that means that at most there will be 2 to the, no, this is, so I cannot reach that. I think my mapping is a little off. So yeah, so this is a bound of the number of possible columns, and this is 32. So it's a little lower than the 48, but still this is not a tight bound. I'm not gonna dive into how to count this. That would be, I guess, a little off topic, and I have to think about it. We can do this in a future stream. But yeah, it's interesting that here the number is lower. So we have to review when we said here that the number of yes, here we added a 50, which was the number of transitions, but that could be dropped to 30. It's not gonna make such a difference in this case, but if we find a tighter bound, it could make a difference. In any case, it is difficult to generate them without trying all of them and check them. So even if we counted them, if our code still goes over all of them, then that will be the cost of the execution of this function. So it wouldn't help a lot. So yeah, I think that's all I have for now of this one. So let's review. So we read the problem, we realized, so it's a counting problem. Sometimes counting problems can be, not only optimization problems can be solved by dynamic programming, counting problems can be solved by dynamic programming as well. We notice that you always need to look at pay attention to the constraints that's necessary to pick up an effective algorithm that is as simple as you can make it. We notice this asymmetry, which is huge. The number of rows is at most 5. It's very little. So that made us think that maybe if we filled by column, we only need to remember very little information, whereas if we fill by row, we need to remember a lot of information. So that means that there are overlapping subproblems. So that's why we use dynamic programming to solve it. Then we said, okay, there's little information, but how many exactly possibilities are there? So we use combinatorics to count them exactly. It turned out it was 48, very little. And then we thought about how many subproblems there are, and how many transitions, what's the total order of complexity of the dynamic programming. So we counted that, we bounded by 2.5 millions, which is good enough for LeetCode. And then we wrote the code, we wrote this helper functions for checking if a mask was valid. We said that we will encode this in digits of base 3, so base 3 encoding, because that would help us to memorize the previous column. Since it is a number, that's easy to cache, to use as a key in a hash. If it's a list, and it's faster also. It's more efficient. If it's a list, then you cannot hash it in Python. Use it as a hash key. And then we just, we created this function that deals with the mask and checks whether there are consecutive digits that are equal, or colors, as we interpret digits here. And then we did another that gets two adjacent columns, and checks whether the corresponding cells match. If they match, if they're the same color, then it's not valid, and if you don't find a conflict, then it's valid. And so we filter the ones that are not valid, and we call recursively for the next column, and that was non-column. Rest in peace. What do you mean? The problem rests in peace. So yes, that's the review. The stream break-in. Oh, I'm not checking the metrics, frame drop or what, or whatnot. Oh, so there was a cut. Anyways, I was just repeating myself, so I guess it doesn't matter. I don't. Well, the recording should. Oh, no worries. Okay, great. Yeah. So I guess the record. I'm doing LeetCode problems with Java. Do you recommend switching to Python? Thank you for the in-depth explanation. Yeah, that's my goal. Thank you for your support, and yeah, fire away if you have questions. So Andrew, yeah, that's a tough one. I guess depends on how familiar you are with Java. If you are already very familiar with Java, then it might not be worth it to switch to Python. I guess it also depends what your goal is. If you're preparing for interviews, then I will suggest to keep to stay with the language that you feel more comfortable with. Yeah, Python has lots of advantages for interviews, so you have to evaluate the trade-offs to make a choice if it's worth it. Java devs get paid more than Python if you switch to Python, but it takes time to excel at it. Yeah, those are different things, right? If you want to, so there are companies that will let you use any language in the interviews, regardless of what you're expected to use in the job. Like I think Fang is like that. Oh, only to LeetCode like for fun, like I do. I mean, if you want to compete, well. Those are strong words, my friend. Yeah, it's very subjective. I mean, it's always good to learn a new language, especially Python, which is very useful, not only for job, but for automating things and for prototyping things. So if that's the case, then I would recommend you to learn Python. Java is a lot more verbose. Java at the moment, and I like that, but to do LeetCode problems, I'm thinking to learn Python. All right. Yeah. Yes, to do LeetCode, I would say Python is better than Java. In the sense that those are strong words, bold statement, but Java tends to be very verbose for writing very concise solutions, and that's one of Python's strengths, that the code tends to be very short and concise once you master it. So that's a big advantage, even for doing LeetCode for fun or for interviews or for competitions. Java has the advantage of being faster runtime, but if you're doing LeetCode for fun, teaches in Python and Java, not in Java. I do know Java, but I haven't used it in a while, and I do like Java, actually, but more for more industrial kind of programming, where you want more static checks. But for LeetCode, I think I'd say that overall I will give the advantage to Python, and also as a learning experience, it's a good way to learn new languages, to solve LeetCode problems with the new language. So in summary, yes, yes, learn Python. I would recommend that, with all the caveats that I already said. Anyways, this is getting too long and we are off topic, so I'm gonna end the stream now. So I hope you learn from this not only how to solve this problem, but how to tackle it, how to analyze order of complexity, count things. Yeah, so thank you, Smart Coder. See you later. Bye bye.